Well, welcome back. This is lesson 7 in Math 222 at SUNY Geneseo. And the topic is L'Hopital's rule, but more. And the idea today is that L'Hopital's rule is a tool. It's a tool we use to evaluate limits. But just like when you figure out that your hammer can also be used as a meat mallet, or vice versa, your meat mallet can be used as a hammer, we're going to find out that L'Hopital's rule is useful for finding limits, but not just the 0 over 0 or the infinity over infinity. And so here we go. Let's find the limit as x approaches infinity of x times the tangent of 1 over x. X times the tangent of 1 over x. This would be a limit where as x approaches infinity, the first part is infinity. Well, the first part tends to infinity, and the second factor tends to 0. I mean, that's 0. That's 0, 0. So what happens when you take something that's really, really large and multiply it by something that's practically but not exactly 0? Who wins? Well, sometimes the infinity wins, and sometimes the 0 wins, and sometimes it's some neutral third party like Switzerland. So let's consider what L'Hopital's rule would do for us. L'Hopital's rule can only apply if you have a quotient, because L'Hopital's rule requires 0 over 0 or infinity over infinity. So what we do is we say this is a product that's not useful to us, but if we rewrote it, like that, now we have a quotient, and the numerator goes to 0, and the denominator goes to 0, and L'Hopital's rule applies. So we rewrite a product as a quotient where we kick that x down into the denominator in such a way that now I can use L'Hopital's rule. Well, I don't remember how to do this, so I'll just stall by going down bottom. The derivative of x to the negative 1 is negative x to the negative 2. That stalls for time. Derivative tangent something. Derivative tangent something is secant squared of that something times the derivative of that something. Oh, wait, we already figured out what that was. And so this is going to be easy. And as x tends to infinity, this tends to 0, and the secant of 0 is 1. So I can use L'Hopital's rule if the limit is not a quotient, but it can be written in the proper form. And that's exactly what happens with example 2. I'm going to find the limit as x approaches 1 of 1 over ln x minus 1 over x minus 1. A problem that you might think is a bit bizarre because as x tends to 1, this tends to some large number. This tends to some large number. So what happens when you take infinity and subtract infinity? Who wins? Well, sometimes infinity does, and sometimes negative infinity does, and sometimes it's 0, and sometimes it's something completely different. L'Hopital's rule does not apply to this because this is a difference, but I know how to combine fractions where the denominators are different, and so do you. You get a nice common denominator and a numerator to go with it. This is a problem where the numerator tends to 0 and the denominator tends to 0. So we can use L'Hopital's rule. And L'Hopital's rule says we take the derivative of the numerator, that's 1 minus 0 minus 1 over x. The derivative of the denominator now, that's tricky because this is a product rule. The product rule is so much fun. It's 1 prime 2 plus 2 prime 1. That sounded really bad. So as x approaches 1, this part goes to 0. And this part also goes to 0. No! Yes. So we try again. Derivative of the numerator is now well established. The derivative on the denominator turns out to be a mess. Bottom times derivative of the top minus the top times the derivative of the bottom. For the rest, you won't be scared. Over the bottom square. This is calc, this is calc, this is calc. Oh, and don't forget there's a plus 1 over x hanging out because the derivative of ln x is 1 over x. So now what happens? Well, you multiply everybody through by x squared, and you get 1 over x squared multiplied all the way through. I know there's a plus x at the end, and then you just get this. You get x minus 1. And so what happens as x gets closer and closer to 1? Well, this thing turns out to be 1/2. So even if it doesn't look like it's a L'Hopital's rule problem, it could still be. That possibility exists. A little bit tougher to see in this scenario how L'Hopital's rule would be helpful to us, but I again maintain that it is helpful to us. But it's helpful to us by considering the following instead. Let's consider instead the natural log of x to the 1 over x minus 1. Why would we do that? Because if we consider the natural log, what happens to that power? Right. That power comes down in the front. We used natural log properties to do such a thing. So the limit as x approaches 1 of the natural log of x to the 1 over x minus 1 is, by laws of logs, the same as 1 over x minus 1 times the natural log of x, which is, by algebra, that. Now, as x tends to 1, this tends to 0, this tends to 0, we may use L'Hopital's rule here. So, derivative of the numerator, derivative of the denominator, and try again. Oh, this is much better. That's 1. So here's the catch for us. Here's where we have to make the jump. The natural log of the thing we want goes to 1. So what about the thing we want? If the natural log of the thing we want goes to 1, then the thing we want goes to e to the 1, and that's e. And mind you, this 1 is that 1. They are the same 1. So the limit that we're looking for is e, and we figured it out with L'Hopital's rule, but we did it using a natural log because that was helpful in bringing an exponent down. See, otherwise, this is 1 to the infinity, and who knows what that is. In this case, it happens to be e. Well, I'll try that one more time. We'll see if you can keep track of all the steps. We'll find the limit as x approaches 0 from the right of x to the x. And again, that's a tricky question because you have 0 to the 0 power. Well, pretty much anything to the 0 power is 1, but 0 to pretty much any power is 0. So what do you do with that? Well, you consider instead the natural log of x to the x. And why would you do that? Because the power comes down in front. So the limit as x approaches 0 from the right of the natural log of x to the x is the limit as x approaches 0 from the right by laws of logarithms of x times ln of x. That is a product. L'Hopital's rule does not apply to a product, so we need a way to rewrite this as a quotient. Well, I like ln x where it is. How do we bring the x into the denominator? That's right. Now we can use L'Hopital's rule on something that is infinity over infinity. L'Hopital's rule says take the derivative of the numerator and the derivative of the denominator and try again. Well, no surprise, this turns out to be 0. So if the natural log of the thing we want turns out to be 0, then the thing we want has a limit of e to the 0, and that's 1. I'll go one more. We'll do one of the infinity to the 0 variety. We'll find the limit as x approaches infinity of ln x to the 1 over x. This tends to infinity. This tends to 0. So I take a base that's getting larger and larger and larger and raise it to an exponent that is getting smaller and smaller and smaller. So how does that go? We consider instead the natural log of ln of x to the 1 over x, and we see where that takes us. The limit, sorry, it's not equal. These are not equal. This does not get an equal sign. Limit, x approaches infinity, ln of ln x to the 1 over x. Well, we know from algebra that this 1 over x can come down in front, and if it comes down in front, it's really there. And now L'Hopital's rule applies. L'Hopital's rule says I take the derivative of the numerator and put it over the derivative of the denominator and try the limit again. The limit is x approaches infinity of f prime over g prime. And as x gets larger and larger, this is basically 0. This is basically 0. This whole thing is practically 0, which means that this tends to e to the 0, and that's 1. And so we have 5 different examples of L'Hopital's rule coming to our rescue in scenarios where we would not have expected it to. So, some things for you to try before we gather. This would be where we kick off next time. So if you're curious, in numerical order, the 3 answers are 0, e to the minus 2, and e to the 4. Those are the answers in increasing order. The question is which of these matches up with which of those, and I'll let you consider that in the privacy of your own dorm room. So there you go. Thanks, everybody. See you next time.